So we start the first half of the afternoon's presentation today, and I have an important announcement. So at the end, please don't leave and instead line up in front of the Wolfenson Hall for a group picture. And it is very important that everybody lines up according to their height. So vertically challenged people like me should be in the front. Yeah, and we will remind you again at the end. Now, at the beginning of the session, we have a very special opportunity today because, you know, everybody, even Jean Bourgain, has a teacher. And yesterday, we've heard some fascinating stories about Jean's parents in Vitaly's talk. But we are very lucky that Jean's PhD advisor, Freddy Delbaen, is here himself, and he will say a few words.
Okay. Sometimes I ask whether people can hear me, but I don't do that anymore because the last answer I got was no, but it doesn't matter. So okay, good. The first time I saw Jean was when he was a student, and it was clear from the beginning that he was a very strong mathematician. And of course, we could talk about his life at the university and how he was doing mathematics there. I will not go into these stories. I will not talk about Jean and the wine cellar of his parents. Some people know what happened there. And I'm not going to talk about Jean and the new coffee machine in the Department of Mathematics. And I'm not going to talk about Jean and how helpful he was when we first visited Poland and needed to buy train tickets to go from Krakow to somewhere in the south in Poland. So I'm not going to talk about all these stories and some nice stories. I'm just going to talk about the so-called Bourgain-Delbaen space and how Jean solved this. What happened was that I was working in Banach space theory, and we were looking at the scriptal infinity spaces. And this was, of course, the basis of this was to be found in Joram Lindenstrauss' book. And there were several conjectures. And I worked on some of these things, couldn't prove any of them. And then so I took a strong conjecture, then weaker and weaker and weaker. Finally, I worked on the so-called weak compact extension property. For those who don't know what it just means that if you have an operator which is weakly compact, defined on a subspace of another Banach space, then you can extend it to a weakly compact operator defined on the whole space. Of course, this property depends on the range space, and well, everybody believed that this range space, which you can easily show that it must be scriptal infinity space, that such a space could not exist. And so I was working on that, and I had a lot of properties that such a space should have. And the more properties I could find, the more I got convinced that such a space was very crazy and that it could not exist. Jean, at that time, he was working on a more durable problem. He was working on L1 spaces. And so one day, during coffee break, he came to my office and said, what are you working on? And I said, well, I explained what I was doing, or tried to do. And then, okay, Jean started to talk about it, so we had a little discussion. And so he asked me, well, if you do this and this and this, do you get a scriptal infinity space? And the answer was true, you get a scriptal infinity space. So after this small discussion, Jean said, well, okay, I go to my office. So he took his coffee, I took my coffee. And I think about 10 minutes later, he came back. And he said, I think I can make you a Schur space. Now, for those who know this kind of theory, scriptal infinity and the Schur property, they couldn't be good friends. So it was clear that that would be a very, very, very stupid space, in fact. But he came up with this thing after 10 minutes. And okay, if somebody would have told me that, I would say, sorry to say that, but you know, hate to say this at your age, but Santa Claus doesn't exist. But Jean had done several things, and when he said he could do something, most of the time it turned out that it worked. And so I believed him, and the next day he came up with the details, and we checked a couple of other properties that we thought that this thing could have, and that was true. So this space then later was used by many other people, and this technique of making this Banach space, which is entirely due to Jean, was used over and over again. So if I look at this time investment, because I'm now doing mathematical finance, so I look at the return on things. And so if I look at the return on the time investment of Jean, it's probably the best investment he ever made, because in 10 minutes he could solve a problem that kept a lot of people busy for many, many, many years. And that paper, well, is now cited in many, many other papers. So I think it is, on time efficiency, the best investment Jean ever made. We had another paper in common where we worked a little bit together on that, and we knew how to do that. But when Jean started to write, it turned out to be something completely different, and of course with a lot more elegance than what I had in mind in the beginning. So that was Jean. You gave him a problem, and then he started to work on that, and then of course immediately after that he found a solution. And that is for a lot of people this was. I know that a lot of people were afraid to tell problems to Jean, because they were afraid that he would the same evening come up with an answer they were looking for in years. So that is. But Jean was very, very generous in his ideas. As I said, as a student, he was extremely, extremely good. It is. I was not teaching in the bachelor program, I was only teaching in the master program, so I only learned about this very strong mathematician when he was already in the third year of the mathematics program in Brussels. And so we prepared some special exercises and gave these exercises to the students, and of course Jean could solve them in a couple of minutes. But that was not the most important thing. More important was the way he solved them and the elegance in the answer he always could come up with. That is, I can go on for many more minutes and tell stories about the daily life and so on. I'm not going to do that. I just want to say that it was a pleasure to have him as a student, of course. It was also a pleasure to have him as a friend. So thank you. Thank you.
All right, so the topic for the, for the first half of this afternoon is quasi-periodic and a little bit other Ergodic Schrödinger operators, and it only has one but really excellent featured speaker, Wilhelm Schlag. But because of that, Gigliola Stafilani, who is the real boss of this conference, has asked me to give a little more extended introduction, so that to add some further perspectives on Jan's impact in this field. So you see this picture, oops, it was too fast. This picture is made in 2001. This is about the time when Jan was most actively involved in this area, and you see how happy he is working on quasi-periodic Schrödinger operators. So let me just very briefly introduce the setting, and I will not give any details, and Wilhelm will take care of that, and he's a great explainer. So, but basically we look at discrete operator acting on L2 of ZD, discrete Schrödinger. So you take your favorite Laplacian discrete, and you take a potential that is given by the values of some real-valued function along the trajectory of an ergodic action of ZD. So that is the key setting, and in this case, spectrum and spectral components are the same for all phases. The theta is called the phase here. But still, there is some fascinating dependence on the phase, as we will see pretty soon. Now, this should not be viewed as a discretization of continuous Schrödinger. Actually, discrete Schrödinger appear as a model in their own right in solid-state physics, that is so-called tight-binding model. And in particular, the two specific classes appear very prominently in physics. These are quasi-periodic operators. That's when your ergodic action is a rotation or a group of commuting rotations on the torus, and Anderson model. That's when the values of the potentials are high IDRVs. So ergodic operators feature really exotic spectral properties, and basically think of something bizarre that you think will never happen spectrally, and it turns out that you will find it in this class, and maybe it will even be generic. And that's what makes them really attractive to mathematicians. But of course, also special attraction comes from their connections to physics, and actually being models coming from physics, especially those two, quasi-periodic and random. So they provide these two models theoretical foundation for 3 Nobel Prizes, and are also related to a recent Fields Medal. Now, let us switch to specifically quasi-periodic operators. And here, if you think about it, it is specifically, it is a model case of a small denominator problem, because it is natural to approach this as a perturbation problem. When lambda is small, it is a perturbation of the pure Laplacian. When lambda is large, it is a perturbation of the pure diagonal. So you may expect that perturbation theory will somehow work, but it is a classical case of small denominators, of the need to find them, and small denominators are governed by ergodicity, and actually ergodicity quite related to number theory in this particular case. And so basically it was probably one of the first cases when KAM was successfully applied in the pioneering work of Dina Bourgain-Sinai back in the 70s for small lambda. Now then, a completely different but also KM type scheme was developed by Eliasson in 91. Reducibility, of course, developed the theory of reducibility of cocycles. For large couplings, also there were powerful KM type methods developed by Sinai and Fröhlich Spencer-Whitwer in the late 80s, and then also Eliasson. So I, again, will not talk more about this topic because I suspect maybe Wilhelm will say also a little. But what John has brought into this field is he entered this field around the turn of the century, was, so the first thing he brought into this field was robust non-KM methods, basically based on direct estimates of the Green's function in the regime of, well, basically in the large coupling regime. So again, I don't want to explain the details because he mainly, at least the original works all came with co-authors, mainly Michael Goldstein and Wilhelm Schlag, with whom some of the most powerful work was done, and he was a young postdoc at the time. We also had a couple of papers, but basically, so I will not explain why non-KAM is a virtue here, but it is both in the kind of results that were obtained in cases where there were previous results, and in cases that results by KM methods were simply not possible before. And there were also powerful application to random nonlinear Schrödinger, partially with Wei Min Wang, who is here. And all this is, much of this is presented in Jean's book, published about 10 years ago, Green's function estimates for lattice Schrödinger operators. Now, I wanted to say a few more specific words about two other aspects that came out of this. So one is that Jean, at about the same time, had a series of very nice papers with a number of corollaries of this Green function estimates. In particular, one corollary was massiveness of the spectrum in certain sense. Again, I will not give more detail here, but what makes it nice is that some further modification of that is actually allowed us very recently to obtain first results on absolutely continuous spectrum for multidimensional quasi-periodic operators at low coupling. And this is work in progress, joined also with Leonid Parnovsky. The second one I wanted to talk about is the result on continuity of the Lyapunov exponent of analytic cocycles in frequency, at irrational frequencies. So this is actually an optimal result in two ways. So first of all, Lyapunov exponent can be and typically is discontinuous at rational frequencies, and also analyticity is crucially important for this result, as follows from recent work by Wang and Yu. So this has had an important prequel, celebrated paper by Goldstein and Schlag, where they developed methods to prove continuity of Lyapunov exponent and use them to establish Hölder continuity in energy for Diophantine frequencies. So we took some ingredients from their work, but the point for us was actually the continuity in frequency, and it required some very delicate analysis, took a lot of Jean's ingenuity. I was just telling Yasha Sinai about this after lunch. So why do I want to talk about this specific work? Mainly because of the sequels. So it turns out that this work was crucially important for the solution of Ten-Martini problem. That was work with Avila. And even more strikingly, for Avila's global theory of quasi-periodic cocycles, which basically starts with approximating of Lyapunov exponent at rational frequency with those at rational frequencies. So I actually talked to Arthur Avila yesterday, and he asked me to say specifically that he entered in this field in the early 2000s, but after all this original development by Jean, after reading Jean's papers. So specifically, he was reading Jean's very first paper with Michael Goldstein and this continuity paper, and he said that this was kind of an analysis unlike what he has ever seen before, and it got him excited, and it motivated him to enter into this field. He thought that that was something that he should do. And so I should say also, actually, about myself a few words. So when Jean entered with his work, it was about the year 2000, I already had some results in this field, and originally I felt just like Gilles Pézière described yesterday, like basically what can I do now? I just have to close shop. But at the end, it proved a huge blessing for me personally, not just because I got to collaborate with Jean, but simply because the exposure to his work and his methods, I think, was really transformative for me. And also, it was a fantastic blessing for the field, definitely, because it opened up so many new things. And then going back to Avila's work, so definitely Avila's entrance into this area was also another blessing, and it is remarkable that Avila actually entered into the field motivated by Jean's work without ever meeting him at that time. Okay, I also want to mention Jean's paper in 2005 where he proved continuity of Lyapunov exponent for multi-frequency operators. And this is a paper that I think has been ahead of its time. I think it's still not very well understood, but we're working on that. Okay, I want to mention a couple of other aspects. So one is Jean's work on Bernoulli-Anderson model. So Anderson model is the one with IIDRV potential. And in the regime of large coupling, so that is, one expects Anderson localization, and that has been essentially solved back in the early 80s by very powerful method multiscale analysis developed by Froelich and Spencer that was later perfected by Abel Klein and co-authors over the years. Then there was another method, fractional moments, by Eisenman, Molchanov, and co-authors. Both these methods basically solve the problem fully, but under one condition. They both required continuity of the underlying distribution of randomness. So they did not work for Bernoulli random variables because they somehow, in one way or another, relied on certain continuity of the allowed rank 1 or compact perturbations. And this problem was essentially open for, well, since 83, I would say, so for 30 years until the work of Bourgain and Koenig, who did prove localization. And again, for discrete model, large coupling corresponds to bottom of the spectrum for the continuous model. So they proved localization near the bottom of the spectrum for continuous operators with Bernoulli potential. And this required some combinatorial arguments that actually looked completely outlandish to everyone in the field, but just listening to Avi Vigdorsson talk, I realized that it is basically all very, very related. Another important ingredient was the unique continuation principle. And this does not work for discrete operators. So I should say that the problem, I should remind Jean that the problem is still open in the discrete case, which I think is a complete shame. Okay, so and one more work, and again, I am only talking about some true highlights here. One more work I want to mention is that on the integrated density of states. So back in 1985, Barry Simon published a paper called 15 Problems in Mathematical Physics, where he listed a bunch of problems. And one of those was pretty fundamental. Prove continuity of the integrated density of states for continuum operators. And for continuum ergodic operators. Such continuity was known, and it's a half a page argument for discrete case. So it's kind of an opposite situation from the previous slide. But for continuum, so since 85, it has been a problem. And again, Bourgain and Abel Klein, who is here, proved it in dimensions 2 and 3. So again, this was almost 30 years after the problem was bugging everyone in the field. And again, I should remind Jean that it is still open in higher dimensions. Okay, so I'll take a few more minutes to mention one more result that is actually not Jean's, but it illustrates a current standing of some part of the field, and you'll understand at the end why I'm talking about it. And I want to say a few words about the almost Mathieu operators. And that is a particular case of one-dimensional quasi-periodic operator when potential is given by the cosine function. And it is somehow the prototypical one-dimensional quasi-periodic operator, and it is the one that is coming from physics, from two-dimensional electrons in magnetic fields, the one related to quantum Hall effect and Nobel Prizes, and also to this famous picture of Hofstadter butterfly. So I will talk about arithmetic spectral transitions for this model. So what do we know by now? So first of all, there are 3 parameters here, lambda, alpha, and theta. And if lambda is less than 1, it is known that this operator has purely absolutely continuous spectrum for all values of 2 other parameters. Again, it is a long history, but final results, I will only be mentioning final results here due to Abel. Now, for lambda bigger than 1, the picture gets really fascinating because there will be arithmetic transition depending on the arithmetic nature of both of these parameters. And actually, Barry Simon claims that Peter Sarnak back in the 80s was the first one to predict that things will depend on the arithmetic nature. So that's his claim. Anyway, let us introduce 2 parameters here. First, beta of alpha, that is basically the rate of exponential growth of denominators of continued fraction expansion of alpha. Here, the norm means the distance to the nearest integer. And delta, that depends on both alpha and theta, that is given, again, by exponential rate of approaching of 2 theta by the trajectory of an alpha. And we'll say that alpha is Diophantine if beta is 0, and that theta is alpha Diophantine if delta is 0. This is just slightly more general than traditional usage of this word Diophantine. Okay, so, and then it turns out that there is a sharp transition in both alpha and theta at these 2 parameters. In particular, for Diophantine alpha, there is a sharp transition at e to the delta, and for alpha Diophantine theta and any alpha, there is a sharp transition at e to the beta. So basically, it's a problem that initially was approached by KM methods. When you obtain, you just throw away basically everything that you don't like and obtain some results and hope that you did not throw away too much, and ideally obtain results for full measure. And by now it has transformed into basically essentially a number theory problem where you give me these parameters theta, alpha, and lambda, and I tell you exactly what happens. Moreover, in both cases, throughout the point spectrum regime, one can define precisely the asymptotics of eigenfunctions. So exponential asymptotics of eigenfunctions. I can tell you precisely how the eigenfunctions behave. Basically, it's some non-trivial behavior governed by the continued fraction expansion. And this, again, has had some history, so in particular, just to put it in perspective, in the 10 Martini paper, we needed a localization result, but we could only prove it in this regime. So this is to illustrate that it is non-trivial. When I sent this paper to John, his reaction was that it looks like it is not entirely trivial. So, so why I'm saying this? Well, first of all, of course, I want to advertise it, but my main reason is that I wanted to talk about my young co-author, Lu. Let me embarrass him. He's here in the audience so that you can recognize him. And I first have seen Vincai's paper on the archive a couple years ago when he extended some of our papers with Avila, papers that are very difficult technically, the one that I thought I was doubting anyone would ever read fully, but he clearly did. So I got impressed. I invited him. He was a graduate student, and when I met him, talked to him, it turned out that basically he learned everything by himself. He didn't have a mentor in this field. So I was very surprised. I asked him, how did you do that? And he said, oh, I didn't know what to do, and then my friend gave me the book. So for 3 months, I would come to my office every single day and spend 10 hours reading this book, line by line, understanding it, aiming to understand everything. And as Chaim Brezis pointed out yesterday, when you read Bourgain, there is a devil in every line, right? And yes, he emerged able to do things indeed, and this reminded me of a quote I've seen on Mathoverflow, where someone asked a question about an inequality in Bourgain's work, and Terry Tao answered this question masterfully, and then added at the end. So he said, incidentally, I found the reading of John's paper as a graduate student to be simultaneously extremely frustrating and extremely rewarding. And well, you can read this, I guess, right? I don't need to read it, right? So when I saw that, I thought, oh, that's exactly how I feel. But then I read a following comment by Bill Johnson, and this encapsulated even better how I feel. So, yeah. So, on this note, I am happy to introduce our speaker.